Alright, so we're going to be looking at linear regressions. So typically what we're going to be dealing with is that we're going to have some data available to us, and we're going to try to extrapolate some relationship from that data, and then we're going to interpret that relationship. So let's say that we have some data on the price of diamonds and the size of the diamond, or the carat size of the diamond. So we have the price of a diamond and the carat size of the diamond. And let's assume that we got some data on this. For a bunch of diamonds, we know the price of the diamonds and we know the carat size of the diamond. Alright, well, looking at that relationship, there might be a line that we think passes through this data set that kind of gives us a good interpretation of the relationship between the price of the diamond and the carat size of the diamond. And then once we have established that there's this linear relationship between all our data that we got, the carat size and the price of the diamond, let's say that we know that this line, the equation of this line, the price of the diamond is equal to 6,140 minus 480. Oh, 1,140 times C minus 480. So the price of the diamond is equal to 6,140 times the carat size of the diamond minus 480. And that is representing this line that we have drawn right here that best fits that data. So let's look at this line. What does this 6,140 mean? Well, that tells us as carat size increases by 1 unit, then we know the price of the diamond is going to increase by 6,140. So that's the slope of this. If we notice this P equals to something times C minus some number, that is kind of like Y equals to MX plus B, but now we're being a little bit more specific on what Y and X equal to. That Y in this time is going to be the price of the diamond and X is the carat size. So the slope of this line that we got right here is saying that for every 1 unit increase in carat size, price is going to increase about $6,140. Similarly, what does this negative 480 represent? Well, that's our y-intercept value. Or another way of thinking about that, if we take it quite literally, is that when carat size equals to 0, what is the value of the diamond? Negative $480. Now, granted, that's a little bit problematic because we're extrapolating outside of our data set, which is a little bit problematic. But notice that the line that best fits this data does contain a negative y-intercept term of negative 480. So it's important to know what this means. And mathematically, it's just our intercept term. If we were to take our interpretation of our model quite literally, that means when carat equals 0, price should equal to negative 480. But as we know, there are no carats in the world that are size 0. Alright, so let's look at some more questions that we might be interested in. We might be interested, hey, if the carat size of this new carat that's not part of our data set is 1.2, we might be interested in what is the price of this new carat that has come into our attention. Well, based on this relationship that we know between the price of the diamond and the carat size, we might be able to make a guess at what the price of the diamond would be, given that the carat size is 1.2. So we can just plug in 1.2 for C, and then we can solve for P. So P equals to 6,140 times 1.2 minus 480, or P equals to, if we solve for that, the price of the diamond, it would be about 6,888. So similarly, so here we knew the carat size and we made a guess at what this new carat price would be. Let's make a guess that, hey, if somebody only has $4,000 to spend on a diamond, what carat size should this person expect to be able to buy? So if we plug in 4,000 for P equals to 6,140 times the caret size minus 480. We can solve for C, and when we solve for C, we're going to get about 0.73 C. So we could expect to get a caret size of about 0.73. Alright, so let's look at this next question. Table 6 lists U.S. fossil fuel consumption as a percentage of total energy consumption for selected years. So here's the table that we are looking at, table 6 right here. We can see we have a column of all the years that we're looking at. So we're looking at from years 1985 to 2010. And the percentage of total energy consumption that's based off of fossil fuels was 86 in 1985, 85 in the year 1990, 85 in the year 1995, all the way down to, in the year 2010, 83% of total energy consumption came from fossil fuels. Alright, so the first question we're going to be looking at is draw a scatter plot of the data that we got. So I'm going to cheat a little bit. Let's put it in the same grid. So notice we're going to go from the year 1985 to year 2010. So let's start this at 85. So 1, 2, 3, 4, 5. 90. 1, 2, 3, 4, 5. 95. 1, 2, 3, 4, 5. The year 2000. 1, 2, 3, 4, 5. 2005. 1, 2, 3, 4, 5. 2010. Alright. And given that our energy consumption, our range is from 83 to 86, I say we start our quote-unquote y-axis at 80. 1, 2, 3, 4, 5. 85. 1, 2, 3, 4, 5. 90. So we got percentage of energy consumption and the year. So year 1985, we consumed 86%. So year 1985, 86%. Year 1990, 85. Year 1995, 85 again. The year 2000, 84. 2005, 85. Year 2010, 83. So looking at this data, if we kind of like zoom in a little bit, we can kind of see that there seems to be a bit of a downward trend if we were to draw a best fitting line to that data set. Alright, we are also told that the model, the linear regression model for this data is y equals to negative 0.09x plus 85.8. So given that we have this y equals to negative 0.09x plus 85.8, let's look at this question B. Interpret the slope of this model. Well, the slope in this model equals to negative 0.09. So what does that mean? So U.S. fossil fuel use as a percentage of So as each year passes on, fossil fuel use as a percentage of total consumption, energy consumption seems to fall by 0.09. Use the model to predict fossil fuel consumption in 2025. Okay, remember, so we have y equals to negative 0.08x plus 85.8, where x represents the years since 1985. So that means when x equals 0, years equal 1985. So x equals 0 for year 1985. Well, that means x equals to 40 for year 2025. So if x equals 40 for year 2025, we can just plug that into our linear regression that we were given. So y equals to negative 0.09 times x plus 85.8. And if we solve that, we're going to get 82.2. So that means in the year 2025, about 82.2% of total energy consumption is going to come from fossil fuels. And basically, we have this data for these years. We have a line that best fits that data. If we extend that line past our current time period to the year 2025, say, we can make a guess on total energy consumption based on this line, this relationship that we had developed between the years passing and fossil fuel use. Alright. The last question we're looking at. Use the model to predict the first year in which fossil fuel consumption is less than 80%. Once again, we are going to have our equation of our line, negative 0.09x plus 85.8 is less than 80. So the left-hand side is fossil fuel use as a function of the years that pass. The right-hand side is equal to that, and all we got to do is set it to equal to 80. And we got to make sure that it is less than 80. So now all we got to do is solve for x. If we solve for x from this inequality that we got here, we're going to get x has to be greater than 64.4, or otherwise known as x equals 65 will be the first year where we are consuming less than 80%. If x equals to 65, then we know the year will be 65 years after 1985. So 1985 plus 65 equals 2050. So the year 2050 will be the first year that we predict that fossil fuel consumption will be less than 80% of total energy. Alright, take care.